All right. Welcome everybody to this PhD defense and
yeah, then you can see it.
So welcome everybody to this PhD defense. Today we have the PhD candidate, Nika Alemahdi, that will give the presentation of her work, the fee sensitivity, a step forward in future fuels evaluation. The faculty opponent today will be Professor Pilar Dorado from University of Córdoba in Spain. In the examination board will be Professor Peter Dalander from Chalmers. We have Professor Jesper Schramm from DTU, so Danish Technical University. And we have Senior Lecturer Elna Engdahl Nilsson. And as you can see, we also have our substitute member, Kerstin Sandhed. And unfortunately, Stina Hemdahl from Volvo couldn't join us. She's unfortunately sick. The supervisor for this work has been Martin Tuner, which is with us on the link. We also have the co-supervisor, Professor Antonio Garcia from the Technical University of Valencia, also online. I am Marcus Lundgren, and I will share this session today. Thank you. So the procedure that we'll go through today, we'll start with the introduction that we have already done. The next step will be that I will ask Nika to say if she found any errors within her thesis. After that, I will leave the floor to you and you will give a presentation of your work. After that, we'll take a short lecture of 10 minutes. And after that session, I will invite Professor Pilar to enter the floor and to lead the position of your work. Then we'll move the questions over to the grading examination committee. And then I will also let you in the audience to give questions to Nika as well on this work. After this, the public session ends, and the grading committee and the faculty opponent, we will meet in a closed session where we discuss and decide on a verdict on the work that Nika has been presenting today. After that, we'll meet in the lunchroom all together. The chairman of the grading committee will give the verdict, and hopefully we'll have some nice lunch as well on the fourth floor. And that's it. So I will start by asking you, Nika, do you have anything in your thesis that you want to acknowledge that you found is not what it was supposed to be?
Yes. Sorry for my voice. The first thing is that paper, the fourth paper is accepted. It was submitted and now it is accepted. And there is a figure 5 in this paper on page 14th of the paper, which has some mistakes and need to be replotted. It has some miscalculations, but I will fix it in the final version of the published paper. Yeah, that is what I have found so far.
Okay.
Thank you.
Then I will leave the floor to you.
Thank you. Thank you very much. Welcome everybody to my PhD defense. I apologize for my voice and thank you all of you for being here. A special thanks to the grading committee and my opponent for evaluating my work. I will start with the title of my thesis. Fee sensitivity, a step forward for future fuel evaluation. I think reading this title, you might think that, what is phi and what is phi sensitivity? Or, come on, future is all electric. Why we even should think about having any fuel in the future? If you have any of those concerns or any of those questions in your mind, then I should say that you are sitting in the correct room at the right time. To define phi, first we need to learn a little bit about this. Fire. Fire is the most exothermic reaction, the most known exothermic reaction in the world. To have fire, we need fuel. Just think of methane, for example, in this case. And we also need some oxygen. And then we need to heat up the system, and reaction will start and fire will forms. A fuel and air can be mixed at different ratios. The ratio that we have here in this, small combustion chamber is called stoichiometric ratio. This ratio is such in terms of chemical properties that is chemically ideal. And during the combustion, all the fuel and air is completely consumed. But it's not always the case. Sometimes we have some extra air that we call it lean mixture, or sometimes we have some extra fuel and we call it rich mixture. The ratio of fuel to air is described using fuel-air equivalence ratio, or phi, which is the title, it is included in the title of my thesis. Fuel-air equivalence ratio is the ratio of fuel to air, in the actual ratio of fuel to air inside the combustion chamber, divided by the ratio of fuel to air in the stoichiometric mixture of that specific fuel. Using fuel or using fire, human beings have damaged the nature and have transformed the nature a lot. But effect of fire on the environment is not the only thing that we as humans have done on the nature. Our beautiful planet have 9 health indicators, so-called planetary boundaries. Those are something like blood pressure or body temperature for us human to make sure that we are healthy or not. And I'm sure that you have heard of climate change, which is the most famous planetary boundaries. And of course, we have the rest also here. We have 5 different levels for those planetary boundaries. And the first 2 are the safe levels. It means if the changes happens during the first 2 levels, the ecosystem and the planet can adopt the change and doesn't get sick. But if the damage exceeds these first 2 levels, then the ecosystem and the planet will feel ill, and it's not normal ecosystem anymore. All human activities, from agriculture to burning fossil fuels and mining, are contributing to damaging the ecosystem and putting all of those planetary boundaries to their thresholds. If I just take a simple example, like transport sector, contribution to the climate change, we are burning fossil fuels. We are mining for rare battery elements, and even building infrastructure for transportation. All of those activities are pushing the climate change to the threshold and making the planet sick. But would it be any possibility to decrease the damage that we are, or decrease the damage that we are putting on the planet and planetary boundaries, but by our activities? Or would it be possible to at least keep this planetary boundaries or maintain our activities in a safe zone that would damage the planet less? But how it will be possible, how we can damage less, and which zone would be safe for us to be active and safe for both us humans and for the planet. Yeah, actually there is a safe zone, and we can decrease these damages, and we can keep it within a safe zone for both planets and human. And this safe zone is actually here within a donut. Yeah, but what does it mean? A safe zone within a donut? Yes, this is the donut model for sustainable development. And if we take a look to the inner circle here, we see the social foundations that are required for having a sustainable society, like water, education, income, job, and other things. I'm sure you can imagine for most of those social foundations, we need a sort of transportation. And the other circle is the outer circle of this model, which is limited by the planetary boundaries thresholds. It means that we should provide for the society, but we shouldn't exceed the planetary boundaries threshold. Then the only safe and just place for any development for us and the planet would be within the donut. But would it be possible to develop a sustainable transport system within a donut? To answer this question, we will follow this list for the rest of my presentation. First, I want to explain for you what I have learned, or a little bit, some of the things that I have learned at least during this research. Then what was the problem that I was trying to tackle? What did I have as tools in my hands to solve this problem or to propose a solution? What solution I have proposed, and what was the solution say? Sorry. Let's start with what I have learned. I knew that resilience is vital for any sustainable system, and diversity is a key factor for resilience. When it comes to passenger cars, diversity means that we must have a fleet with different kind of powertrains. This plot that we have here from Bloomberg, it shows the global share of electric vehicle and internal combustion engine in long term for passenger car. It shows that the internal combustion engine share in the market is decreasing from almost 100% to around 40% by 2040, while the share of electric vehicle in the market from around 0 is increasing up to 60% in the market. But if we take a look on this graph here, we will see the vehicles that we have inside the fleet by 2040. Still over 65% of them have powertrain, have internal combustion engine as the powertrain. I believe with such significant share in the future transportation, internal combustion engine as a technology has potential to be used as an enabler for a sustainable transport system and to help us to transit towards a sustainable transport system. Excuse me. But how? How we should use the internal combustion engine as an enabler? We know that internal combustion engine is a well-established technology. And we saw in the previous slide that it has large share in the market. And we also have the infrastructure already in place. But there are also some small challenges, like we need to increase the efficiency of internal combustion engine further. We need also to decrease the emissions, and we need to replace fossil fuels with renewable fuels. Let us start with renewable fuels. Directly from sun, here we have biomass. And from biomass, using different pathways that sometimes are not that simple, we can produce biofuel and advanced biofuels. The other way is, excuse me, using electricity directly and produce, again, different pathways, using different pathways that are sometimes complex and are not always straightforward, produce electrofuels or advanced biofuels. I have an interesting plot here. It's from McKinsey Global Energy Perspective. This graph talk about different scenarios about future demand of sustainable liquid fuels. And the main scenario that I want to talk about is this one. This scenario basically says that if we aim to maintain the temperature increase of the planet below 1.5, which is based on Paris Agreement, then we need to increase the share of sustainable fuel in the energy sector up to 40%. Then sustainable fuel or biofuel is not just an option anymore or a may, it's a must. But what about the other two? We need to decrease the emissions and we need to increase the efficiency. We have some combustion technologies that have these two properties, something like homogeneous charge compression ignition engines or spark assisted compression ignition engines or partially premix combustion engines. All of those technologies are working based on a concept called LTC, low temperature combustion concept. I apologize. Low temperature combustion concept is interesting because it has low emission and high efficiency, but it also has some drawbacks. As an example, it has a high pressure and low temperature of unburned gas. Therefore, we cannot use the conventional test methods like RON or octane rating for the fuel that we want to use for LTC. They don't work there anymore. Some of the LTC concepts also, technology also have really limit load range, like XCCI. And we also face some controllability problem when we work with LTC concept. But these concepts and these technologies are very sensitive to variation of phi, means variation of fuel to air ratio. They are sensitive if you add more fuel or less fuel. And being sensitive to variation of phi means that different fuels with the same RON number still can have different phi sensitivity and can have different response in LTC combustion. This is another reason that we cannot use the conventional test method for evaluating fuel for low temperature combustions. But what was the problem? If I want to summarize the problem, Cut the long story short, I knew that we need a sustainable transport system, a resilient, sustainable transport system. I knew that we have internal combustion engine well established, already in place, with a large share in the future. We have LTC combustion as a low emission, high efficiency combustion concepts with some problems. I also knew that we need sustainable liquid fuel in the future, and it's a must. So probably we will have that in place. But the problem was that how we should feed this new fuel that we have to the new combustion concepts that we have, because we don't have the good method, or we don't have appropriate test method to evaluate it, if it fits or not. Then to tailor fuel for LTC engine, we need a test method that can evaluate combustion response to different kind of a stratification, both fuel stratification and temperature stratification. The method also needs to be standard, so it should be possible for refineries or fuel producing industries to use that method. It should be rather technically simple, and it shouldn't be dependent on the complex prerequisite data, such as kinetic mechanisms, because those are not always available. And this method, I believe that if we can produce, or we can develop such a method, then can support the transition of transport sector towards sustainability by providing supplementary knowledge for tailoring fuel or preparing fuel for homogeneous combustions, homogeneous modern combustion, thermal or fuel stratified combustions, and also load adaptive fuels, the kind of fuel that can tolerate different kind of load with minimum combustion instability based on the combustion concepts. And then this method may also give us some information about how to design a controller strategy for low temperature combustion, and also give us valuable information about evaluating fuel, knock resistance evaluation of fuel for SI engine. But what did I have? Yeah, I had access to this beautiful engineering masterpiece, an adorable CFR engine. This is a standard test engine. It's not an engine that you see it normally on a car. It has developed long ago for developing octane rating of the fuel because it has variable compression ratio and it's versatile for burning almost every liquid fuel. And the CFR engine that we had in Lund, normally CFR engine is equipped with a spark plug and it's spark ignition engine. But at Lund University, we had modified this engine for HCCI combustion because we want to do auto-ignition studies. You see some of the specification of the engine here. It is single cylinder engine. It has variable compression ratio from 4 to 18. And yeah, these are, I think, the most interesting things about this engine. But we have modified it for HCCI combustion. But what is exactly HCCI combustion? Homogeneous charge compression ignition is a combustion technology that works based on low temperature combustion concept. inside the combustion chamber of an HCI engine, we have a mixture of homogeneous, almost homogeneous mixture of fuel and air. It is like SI up to here, but then we don't have a spark plug. But how we burn it then? We compress a mixture of fuel and air to the point that it hits up and auto-ignite. Spontaneous auto-ignition starts in whole cylinder in consequences, not all at once, and generates power. And then, like any other engine, we will push the exhaust gas out of the engine. This is how HCI technology works. Let's come back to the test cell. In the test cell, yes, I have explained that I had this masterpiece in the test cell. I also had a sample line to the HORIBA emission analyzer for measuring the measuring different emissions, and also from emission calculating phi, lambda, and oxygen. I also had a sample line, data sample line, to data acquisition system to just from different sensors to measure and save different parameters of the engine for post-processing. The general strategy of my research was that, my experiment was that I had 3 different intake temperatures, one 50 degrees Celsius close to run number measurement temperature, 150 close to man number temperature, and one in the middle. And then the pressure, the intake pressure was ambient. The coolant temperature was set based on run and man, because I'm using the CFR engine, which is designed for this method, so to keep it a standard. And then for different experimental campaign, I had the CA50 constant at different levels, like 3, 6, and 8. And compression ratio was variable. And I also had the equivalence ratio range of 0.25 to 0.4 for different campaigns. It was like this, that I was adjusting, or I was changing the equivalence ratio, and to keep the CA50 or maintain the CA50 constant, I was adjusting the compression ratio. But then, what was the solution that I have proposed? This diagram here is a simplified flow chart diagram that demonstrates the different steps of my research, or my, better to say, method development work. First, using or by some preliminary studies, I defined some criteria for designing the experiment. And then after that, selecting that criteria, I have evaluated the method using some extreme fuels. I will talk later what do I mean by extreme fuels. Then, when I got the results or data, I check them if they are sensitive. It means that if I change the phi, do I really see any changes in the result parameters or not? Is it consistent? How much is the error? Can we rely on this data? If we do the experiment in different days, do we get the same result? Is it transferable? Can we use this method for designing fuel for a conventional engine? Would it be possible to benefit from this result in a conventional engine? Because as I told you, CFR engine is a test engine. And then if the answer of any of these questions was no, I was going back, defining the method again, evaluating again, and all of this step until the answer is yes. And when the answer is yes, finalize the method, test different fuels on different engines, and then that's it. But what kind of fuel I have used? For preliminary studies, I have used gasoline and ignition improver. I have also used different reference fuels at 3 different run groups of 63, 84, and 105 octane number. This is the extreme fuels that I will talk about it more. And I have also tested neat ethanol, neat isobutanol, and neat N-butanol. I have also evaluated the blend of isobutanol with the reference fuel. But let's just have a closer look on the extreme fuels. Here you can see the fuel matrix that I have developed for my experiment. I had these 3 base fuel. I have selected these 3 base fuel first. Ethanol, the highest run number and highest oxygen concentration, no aromatic. PFR 84, a middle run fuel, and PRF 63, very low run fuel. And then based on those baseline of octane number, because I want to isolate the effect of octane number from phi, that was important for me to have fuel in each group that have the same run number but different composition. In each group, I had fuel that has both toluene, aromatic, ethanol, oxygenates, and isooctane and N-heptane. I also had a fuel which has no aromatic, only oxygenates, and isooctane and N-heptane. And again, lastly, fuel which has toluene, but not any ethanol, that has high concentration of aromatics, but doesn't have any oxygenates. But how I did it, we had an in-house model developed by Hadil et al. You can see the link here. First, I estimated the volumes that I need to have such a run number using the model. And because always models have uncertainty, I send it to Seibold company to measure the exact run and mon number for me. And I did the same for other groups. That was for the run 105. Did the same for run 84. First estimate and then measure. And run 63, first estimation and then measurement. I apologize. I'm not the first one who have worked on Phi sensitivity. And I think I will not also be the last one. From the literature review, I have learned a lot about Phi sensitivity. I have learned that Phi sensitivity is strongly dependent on the pressure and temperature inside the combustion chamber. I also have learned that the fuel-air mixture with different equivalence ratio will show different ignition delay when we burn them in a combustion engine. I have also learned that heat release during early reaction is an indicator of Phi sensitivity. Means that fuel with higher Phi sensitivity probably will also exhibit more heat release during the early reactions. There are some terms that I think I need to clarify them, like ignition delay and heat release, early reaction, and so on. So let's start with those clarifications first. Here what you see is two heat release profiles for two different fuels. The black one is single stage combustion, and the blue one is two-stage combustion, both at the same Phi level. If I zoom in to the low temperature reactions here, or early reactions here, better to say, let's start with this two-stage combustion. We need to define the start of autoignition. Based on my research and literature study, I have selected 0.2 joule CAD for start of autoignition. And a start of main combustion, 0.5 joule per CAD. Here, the bump that you see here, this is low temperature reaction, the bump. And the top of this bump here, and minimum of the low temperature reaction here, this gap is called NTC. NTC zone is a zone that temperature keep increasing, but less and less fuel burns. And this minimum point here, end of NTC zone, would be the start of intermediate temperature heat release. From autoignition, start of autoignition to start of low temperature heat release, we have intermediate temperature heat release. We have low temperature heat release and low temperature reactions. From start of intermediate temperature heat release to start of main combustion, we have intermediate reactions that release the intermediate heat also. From a start of autoignition to start of main combustion, we have ignition delay, or the definition of ignition delay that I have used in my work. But what about the single stage combustion? When we don't have any low temperature heat release, therefore we don't have also NTC zone. And the start of intermediate temperature heat release would be the start of autoignition. We don't have any low temperature heat release, we only have intermediate temperature heat release, and the ignition delay would have the same definition, from start of autoignition to start of main combustion. Now we know the definitions that I have in my work. Then let's continue with the bullet point. The first thing was that pressure temperature dependency of Phi sensitivity. Here we have pressure temperature trajectory graph for PRF63 at two different Phi levels. You see that we also have different compression ratio. And by varying the compression ratio, in SCFR engine, the temperature pressure trajectory prior to the autoignition and generally inside the combustion chamber changes. And since you see here that we have different pressure temperature regimes when we change the compression ratio. And since an SCCI combustion is a kinetic driven combustion, it is sensitive to this variation of compression ratio. And therefore, by adjusting or changing the compression ratio in a CFR engine, we are changing the onset of different phases of combustion inside in an HCCI combustion. But what about ignition delay? Excuse me. Here we have the only early reaction part of PRF63 at different Phi levels. We see there also different compression ratio. And this is only one example of the data that I have. And I have adjusted compression ratio to maintain the CA50 constant. And it seems that adjustment of compression ratio to keep the to maintain the CA50 constant as kept also the ignition delay constant. So it means that it compensates for the impact of phi variation and ignition delay. You see that we have almost the same ignition delay at different compression ratio at different phi, because when I was changing the phi, I have adjusted compression ratio to have constant combustion phase. But this is only one of the few. I have normalized ignition delay to be able to have a better understanding of the rest of the fuels. This is the scaled up bar chart that you see here. But the normalization was that basically I have measured the change of ignition delay, the ratio of ignition delay change to the phi variation. You see here, we have different run groups. Excuse me. You have different run groups, and the variation of ignition delay or the normalized ignition delay is less than 0.01%. And if you compare it with the ignition delay of 25 crank angle degree that we had, it is far less than the standard deviation of the ignition delay from the mean value. We can take it like 0. You even see that for those fuel, it is actually 0. But the rest also are statistically 0. Then with high confidence, I can say the compression ratio variation compensates for the effect of phi variation on the ignition delay. But what about the heat release during the early reaction? I told you that in literature, they say when the heat release is higher, then the heat release during the early reaction is higher, then the phi sensitivity is higher. In this plot here, we see different run groups and different heat release during the early reaction, both intermediate and low temperature heat release. And if I bring the normalized compression ratio here and plot it, I see that there is correlation between the amount of heat which is released during the early reaction and the normalized compression ratio. There was not any correlation between this heat release and ignition delay, for example, that we saw in the previous slide. And there is not also any correlation between this heat release during early reaction and auto-ignition temperature, because auto-ignition temperature of HCCI combustion for different phi, it's in such a narrow range that it's not a statistically significant differences based on both literature reviews and my personal work. Looking at this graph, when we normalize the compression ratio and compare it with heat release during the early reaction, we notice that there is a clear link between heat release during the early reaction and normalized compression ratio. Then would it be something to be used as a method definition? Seems yes. If we want to maintain a constant combustion phase by adjusting compression ratio for different equivalence ratio of one single fuel, then the compression ratio variation would work as an indicator for phi sensitivity. And here is the formula for Lund heat sensitivity number, what I have called it. It's important to know that different fuel with the same run number still can have different feed sensitivities. If you look at this graph here, I have plotted the variation of phi based on the fuel composition. And we see that when the ethanol concentration increases, first we have an increase in phi, and then the phi sensitivity decreases. And toluene generally increases the phi sensitivity, and we need a very high percentage of toluene to see any decrease in phi sensitivity. And this percentage is not allowed because the highest percentage of aromatic in gasoline is 35%. That was just for test and experiment. So we will end up here. It means that adding ethanol, adding toluene with the percentage or with this percentage that it's allowed would always increase the phi sensitivity of the fuel. There are different reasons for that. One reason is that small amount of oxygenates enhance the in-cylinder temperature and increases the chance of increases the charge cooling effect and enhances the combustion. But when it's much more, then it leads to unburned, in the range of this study, incomplete combustion or unburned hydrocarbon. And we need very high compression ratio to burn it, to auto-ignite it, because it's HCCI, and the sensitivity of that fuel decreases. But when we have toluene, the thing is that ethanol works as a radical sink and suppresses all of the intermediate and low temperature reactions. Toluene also does that a little bit, but in the other way. The point is that toluene works as a radical sink for low temperature reaction, but also delays the main combustion. Then what toluene does, that suppressing the early reaction and also pushing the main combustion, therefore extending the ignition delay. This is why we will get more phi sensitivity property when we add toluene to a fuel, or aromatics in general. Toluene is just an example. But what Lund sensitivity we want to say, if you want to summarize it in one sentence? Lund phi sensitivity number evaluates the auto-ignition sensitivity of fuel to stratification. Could be both thermal or fuel stratification. Here we have Lund phi sensitivity number measured for the fuel of this experiment for two different intake temperatures of 50 degrees Celsius and 150 degrees Celsius, 323 Kelvin and 423 Kelvin. There are some points about this number. We can measure it at different intake temperature. We don't need to stick on a specific intake temperature. It depends on our need. But then you cannot compare fuels that you have measured the phi sensitivity in different conditions together. You should compare the fuels with the same intake parameters, input parameters. You can also measure it at different combustion phasing. It doesn't mean that it must be always at 3. It could be any combustion phasing before 8, because then 8 is too late and its combustion is very unstable, as my data shows. But then for any fuel, then again, different fuels must have the same combustion phasing if you want to compare them. It's also important to isolate the effect of octane sensitivity run. You can, of course, but the data wouldn't be valuable if you compare fuel with different run number together, because you are taking to the account the impact of run and auto-ignitability of the fuel in your result. It's not isolated from random anymore. Yeah. Something interesting about this graph is if we look at the fuel here, which are red or highlighted in red, we see that they have toluene, ethanol, isooctane, and N-heptane. So they have both aromatics and oxygenates. And despite other fuels that mainly show a decrease, or they don't change much in by increasing the temperature, these three blends, the first one doesn't show, but the second and third, they show decrease and significant decrease in T sensitivity at higher intake temperature. When I say significant, it means that it's beyond the error and it's out of the standard deviation. It's not just that visually significant. So what it says, this basically says that those fuels, even this one, it doesn't get more unstable when we increase the intake temperature for a normal combustion, SI combustion, for example. And the feed sensitivity of it decreases. It shows less variation of ignition delay when we test it at higher intake temperature. That might be some option for some engines that need to work at different temperature and still get just have different output. But now I want to explain that what does it mean exactly when we say a fuel have high feed sensitivity, high Lund feed sensitivity, or low Lund feed sensitivity. High Lund feed sensitivity number, which is indicator of high feed sensitivity of the fuel, means that the autoignition properties are more sensitive to feed variation. These autoignition properties could be pressure, could be temperature, could be ignition delay. And those kind of fuel, if they have high octane rating, then they are suitable for homogeneous charge compression ignition engines, because you can compress it to the high compression ratio and they can tolerate high compression ratio. But when they burn, they don't burn all at once. They burn at with consequence. Different areas of the combustion chamber will start a little bit of different timing. And this property will make the heat release more smooth instead of just having all combustion at once. Also the same for a stratified combustion. We have a little bit lower run compared to ACCI. We need a little bit of lower run number compared to ACCI here. But again, if we have high feed sensitivity, it means that the stratification will work better. So we have more smooth heat release and more consequential combustion. But it's not always the. It is not always nice to have high feed sensitivity. Sometimes we must have fuel with very low feed sensitivity, like SI engine, because in SI engine we don't want knock. We don't want some autoignition happens somewhere that we don't like, and we also want to have high compression ratio to increase the efficiency. So for normal SI engine, spark ignition engine, we need low Lund feed sensitivity number because then autoignition properties are not sensitive that much. And what does this solution says? That was the proposal that I had, a method that I have developed to be able to evaluate fuel property for low temperature combustion in a better way. But what does this solution say? The Lund Fish sensitivity test method is a platform to measure fish sensitivity of new fuel and conventional fuel in a rather technically simple way, which is possible to be done in refineries because all have CFR engines and also fuel industries. And I have selected the standard condition of run and mount tests. This technically simple method would give us understanding of fuel for low temperature combustion and how to tailor them. Therefore, it can facilitate and it can enable the transition of transport sector towards sustainability by providing knowledge. By providing knowledge about different aspects that I have explained in a previous slide also. Something like that for low temperature gasoline combustion, as I have explained, we need a fuel with high Lund Fish sensitivity number and high octane number. Oops, sorry. For designing a fuel which is resistant to knock for SI engine, we need a fuel with high run number and low Lund Fish sensitivity number, as I have explained. And for stratified combustion, we basically need high Lund Fish sensitivity number and and medium run. Excuse me, and medium run. But there was also some knowledge that I gained during this experiment, and it is in my thesis, but due to the time limit, I couldn't present it all here. This knowledge are about intake, temperature, and fuel composition effect on fish sensitivity, and about combustion phasing impact on fish sensitivity, and about the blending fish sensitivity. At low intake temperature, fuel with toluene or aromatics and oxygenated will have maximum fish sensitivity in the similar run group. We don't compare fuel with different run group together. At high intake temperature, aromatics fuel without any oxygenates will show the highest Lund Fish sensitivity number. A retarded combustion phasing decreases the fish sensitivity of the fuel because decreases the pressure inside the combustion chamber. And fish sensitivity is pressure sensitive. Therefore, we will have generally lower level of fish sensitivity when we have a retarded combustion phasing for our test method. And blending, when we check alcohol, we see that similar to run number, the blending fish sensitivity number of the fuel is nonlinear. Yeah, but what could be the option for future work? The modern engine today are mainly working at high intake, or some of them working at high intake pressure and boosted condition. It would be really interesting to find some or to design some method for boosted SCR and SI combustion. I have already actually wrote the method description, but there was not any time during my PhD to finish that method. Also, it would be really interesting and valuable to have a boosted fish sensitivity evaluation. So the fish sensitivity evaluation that I had was in a naturally aspirated condition. It would be valuable to have it in boosted condition to see the effect of boost pressure. And it would be nice to tailor some fuels based on the method that I have developed here, and then test those fuels in conventional engine. That was actually part of plan, but I didn't have time. I didn't have time to do that. Thank you very much.
Thank you, Nika. So we are at the part where we will have the opponent, but first we'll just take a 10-minute break. So we will be back here in 11:25.
Thank you.
Now we're back in business. Welcome back, everybody. So I will leave the floor to the opponent to lead the discussion with Nika.
Thank you. Well, thank you very much. First of all, I think you can hear me well with this. Thank you. So first of all, I would like to thank you to the University of Lund and your supervisors, because inviting me in such a nice event makes me very happy.
That's our pleasure.
Being in Sweden, that is a great country. And also I want to congratulate you and your supervisors for such a nice work. You can be proud of yourself for being able to produce this nice work, and your family should be also very proud of you. So now you just can relax, because it's going to be very smooth. And I got a few questions, because maybe of my curiosity, not because I think your work is not good. So relax. Okay. Just a curiosity, why did you change your co-supervisor to Antonio? You changed it. You had, in the beginning, you had 2 co-supervisors, and then you changed one of them.
Oh, no, I actually haven't changed my co-supervisor. It was always up to the end of my study. I had 3 supervisors. But then when we want to register the thesis, I don't know, for some reason, they told us that you should only have 2. That was why I have my main supervisor asked me to remove the first supervisor and just keep Antonio.
Okay.
Just that was the reason.
Okay.
But I was always benefited from the advices of all of our seniors in my group, and it was not just about being a student of a specific person. We were just working as a team all together.
Very nice. Why did you decide to tailor the fuel instead of doing something to the engine? As there are many old engines in the market nowadays, and they produce high exhaust emissions. So we're keep on going to use this if you tailor the fuel for modern engines, because I understood you were talking that these fuels will be very valuable for lean combustion technology. So what's going to happen with the old engines? Are you going to is it going to be able to be used in old engines as well, and reduce the exhaust emissions?
Yeah. The thing is that first, one PhD student cannot cover all of the area of the research, and my focus was on low temperature combustion as an interesting concept for future, because low temperature combustion has high emissions and low efficiency. And there is the chance that we can combine different conventional combustions with low temperature combustion. Like SI, we can combine SI for high load with HCCI for low load. This is why it's important to know that those 2 combustion concepts have different fuel need. And in case of using that fuel, what should we do? How we should tailor the fuel that fit both, and those kind of things. But of course, I cannot do research about all of the area, but from the beginning, my project was on low temperature combustion.
Okay. And you decided to focus on spark ignition, even if spark ignition are not the most pollutant engines. You know what I mean? we got mainly two basic technologies which are diesel engines and spark ignitions.
Yeah.
So your engine, your CFR, was you adjusted the compression ratio and all this to use it as a spark ignition engine.
No, the CFR engine itself is a spark ignition engine.
Yeah.
But we have removed the spark plug, or we didn't remove it actually. It is in the place, but we just unplug it, so it doesn't work. And we have equipped the engine with 4 port fuel injectors and 4 different fuel pumps to enable it for HCCI combustion. Because HCCI, the reason for that is that in spark ignited engine, you adjust the compression timing by spark plug timing, and you have flame propagation. So you cannot really study what is happening inside the cylinder in terms of auto ignition. And in normal CI engine, we also have diffusion flame. Again, it's not really possible to study auto ignition property. And HCCI seems to be the only kind of engine or combustion technology that we can study auto ignition property of the fuel. This is why we are using HCCI combustion. But the Lund CFR engine, you just need to plug the spark plug again and use it as a CI engine. There's no problem.
Okay. Well, I understood that you have why you selected the sensitivity. I understood very well. But do you think it would be interesting to have more parameters to have a more precise result in terms of tailored not only sensitivity, but maybe, I don't know, something else? What do you think?
Definitely.
Yeah.
Definitely. This is, as I told in my presentation, supplementary knowledge. This is not the only thing that we need. We need run number, we need MON number, we need heat of vaporization, we need physical properties of the fuel, and a supplementary data that we get from field sensitivity research would add value to our research to do how to tailor fuel. Yeah.
Okay. Well, you mentioned that sensitivity is a decisive property for modern low combustion technology.
Yes.
But not only for these, but also for the old engines, isn't it? Or only for them?
In some sense, like for SI engine, as I told, when we have fuel with high feed sensitivity, we may have knock. But the idea is that because generally run number and feed sensitivity are dependent to each other, means that when we have a low octane rating, we have high feed sensitivity. And we don't use fuel with low octane rating, which have generally high feed sensitivity for SI engine. We don't use them. But when we increase the compression ratio to such a high value to just get the most out of our SI engine, then we face problem with feed sensitivity. If our fuel is also feed sensitive, then we will, we'll have knock or super knock.
Yeah. Why did you use these 2 isomers of butanol? Why not others, or why just one of them? Why did you think that testing both would be something remarkable? Why?
Yes, the thing was that I really like to test more and more alcohol, but we had time limitation. Therefore, I selected butanol isomers, especially because they have very close property to gasoline and conventional gasoline. Therefore, it would be easy to just use them directly, and they are not corrosive like methanol, for example. It would be easy to use them directly in the conventional SI engine that we have, also because of the high run number. And these 2 isomers, even though they have exactly the same chemical formula, they have quite different run number. And it was not really, I have studied the feed sensitivity of these 2 fuels, but not to compare them together, because we cannot, because they don't have the same run number. The main reason was that because those have property very similar to gasoline, And we also have a sustainable pathway to produce them. We don't need to produce them in unsustainable ways. There might be some options for future.
The number of papers delivered from your thesis is impressive. I think this alone is just giving you the
Thank you.
you know. But I guess I know the answer, but I would like to listen from you. What is the relation between your first paper with your thesis? Is something that led you to the problem that you wanted to fix up? You know, the relationship with that.
Yeah. The first paper is some preliminary study because I knew the concept of HCCI combustion. I have read it in literature, but I need to have some hands on the CFR engine because CFR engine is not conventional engine. And just adjusting compression ratio, playing around with different compression ratio, different fuel with different autoignitability. Those was really crucial for me at the beginning to know how I can get the most out of this, out of my research. And also I wanted to test with some normal fuel, conventional fuel, to test how much this CFR engine is reliable, which engine speed is the best, or not the best, but it's the most reliable speed. Or for example, the range of compression ratio, the way that I sweep the compression ratio. If I do the experiment in different days, does it impact on the result? And those kind of very basic understanding was very important for me to know before starting the main job.
I would like to seek you for your opinion about this. You were talking about the Paris Agreement and the need to prevent the global temperature to exceed 3 degrees Celsius.
Yeah.
I found a manuscript from Su et al. Last year, in January last year. It was published in Nature Climate Change. And they said that we have already released enough greenhouse gases to exceed the global temperature limit. What do you think?
Yeah, and the point is that even if we keep up to Paris Agreement 1.5, we still will have some irreversible changes, unfortunately, in the planet. So Paris Agreement is just below minimum, but it is what people have heard of it and have some idea about it. It's not the best, or it's not all that we can do for climate change, in my opinion.
The problem is that if these emissions are already released, I think there's nothing to get done.
There is a still. There were some other slides that I could explain that with them. When we look at the time stability model for the planet, where it was, and when it moved to the coordinates that we are in the time stability and temperature area, if we continue producing more and more, maybe I can draw something on this. Maybe I can just here. Maybe
I can.
It is something like that. Would be time. This is stability, and this is something like temperature. When human being development formed on the planet, we were somewhere here in terms of temperature and time, and we were also stable if you just imagine a surface. But then we polluted a lot of emissions and we moved somewhere here. If we were not polluting emissions, we were just following this path and we were here in the temperature. But we have followed this path, but we haven't hit all of the thresholds yet. If we hit all of the thresholds, we will fall here in a hot house zone that wouldn't be possible for Earth to just jump out of it. It is a stable status, but it's not possible for a human being to leave the norm of, or basically the form of life that we have on the planet will not exist anymore. So we are bare. But we're still here. What we can do that, instead of continue this way down, we just redirect ourselves to go there. This is why producing sustainable fuel is important, because we can do a lot of carbon capture by producing sustainable fuel. And we can also store a lot of those carbon. And we can also have a storage for renewable electricity that we produce, because we all know that battery contaminates soil, earth, and it's just contributes to damaging the sustainable development in poor countries like Africa, when the child labor is providing battery for us.
You, well, continuing with this discussion that I am really interested in.
Yeah, me too.
You said using food crops as a feedstock for
Sorry.
using food
Yeah,
crops
yeah.
as a feedstock for biofuel production is not always a sustainable approach. First, the negative possible impact on food security. And I wanted to ask you, what do you think about the use of land for coffee, drinks? What do you think? Because we are always having concerns about using land for energy, but we have never concerns about using land for coffee. You know what happened? What happened in Cuba, for example, with the coffee they produce. When the prices are going to be very low, they just sell the coffee, and the companies just throw it in the ocean to have the price in a acceptable level. So they are not producing their own basic food. They're just producing coffee for other countries. Let's say other countries. What do you think? Do you think there will be also some regulations for this non-basic food that is produced in land, or we just need to to be careful with the use of land for energy? What do you think?
I think we must be careful with consuming. Again, I need to explain something. We need to be careful with using our resources for everything, not only for energy. Transport sector is just one example that we have talked about it today. This is why we talk about the donut model. We should ensure that people can provide the basic needs, and transport is basic needs for some people, but coffee is not. And then we should also make sure that we don't hit the thresholds of planetary boundaries. Something is very interesting. We all think about having electricity more and more to heat up our swimming pool, for example, here in Sweden. But then people in some countries, kids, even don't have electricity to light up their houses and just study. And with only, if the number is in my mind, with only 10% of electricity that we are using in, let's say, rich countries, we can give electricity to all those countries that they don't have access to electricity, the basic need. So a lot of things could be done. And then we need politicians to listen to scientists.
Yeah. Back to the core of your thesis.
Yeah.
It worries me a bit, but I'm sure you're going to give me the right answer. That the engine speed range has been narrowed so much, because engines usually work at higher speeds. What do you think? Do you think your results may high realistic engine behavior or not? They can just be used in an engine working under a higher speed without any inconvenience?
Yeah, the thing is that, as I have explained, the CFR engine is not a conventional engine, it's a test bench. And when we have a test facility, we try to signify it's like using a microscope. When you use microscope, okay, you cannot see that you have some virus on your hand, but when you put it under microscope, then you see them. It doesn't mean that your hand is clean, but you just don't see it. This is exactly what happens when you do with a test engine. You try to amplify the things to be able to capture them. But it doesn't mean that if you look at a conventional engine, then you don't see that, because those are fuel properties. This is not combustion property. This is fuel property. This is why it's important to not do it in SI or CI engine. Yeah.
I don't know if this is, I guess it is maybe a mistake in the test in table 4.1. You have table 4.1 page 41.
Yes.
Gasoline flash point shows negative values. This is
Yeah.
wrong. Okay, don't worry.
Yeah.
This is something that on page
And also the molecular rate. I think it's maybe, oh no, it's not negative.
the molecular is
Yeah,
is
I think it's also that one, maybe because the font is too small. It's not visible. Yeah, it's the approximation sign. Yeah, sorry for that. Yeah.
Don't worry. Yeah.
Because why? I'm sorry. Why for gasoline is approximation? Because gasoline doesn't have fixed molecular property. It is just hundreds of different hydrocarbons. So you cannot say exactly, this is why I have approximation sign.
Okay. Why did you divide the blends to different row numbers instead of month numbers? You use the row number to divide the blends in different categories.
Yeah, exactly. Exactly. When we want to measure phi sensitivity, we knew that phi sensitivity is more significant or is more visible at low intake temperature. And run test method is measured at low intake temperature. But when you look at MON test, you kind of excluding the effect of heat of vaporization for the fuel. That was why I have used one.
Okay. On page 53, table 5.2.
5.2, yes.
Yeah, you say the crank angle degree is 3.
Yeah.
With a variation of 1. This is too high. What do you think? Variation is too high for a number so small.
Yeah, I can see that.
The measurement, you couldn't do better with the equipment you have. Maybe you couldn't.
Yeah, the thing is that I haven't included any data that has this variation, but this is the variation that we get. But I always try to keep it below. But anyways, the thing is that because we are running HCCI combustion, and HCCI combustion has really sensitive response to the engine condition. This is unfortunately what we get. That also have it with other people who were working on the engine.
This is because this thing I didn't understand very well. You say you were talking page 52 about table 5.1, and you said page 52 is the previous.
Yeah.
You said, as an example of naming convention for the blends, T20, E40, and 10 is a blend consisting of 20% toluene, that is okay, 40% ethanol, and 5% NF10.
Oh, sorry, it's a typo. It's a typo. Sorry,
okay,
I didn't notice that.
Because I was thinking all the time.
No, I'm sorry. It should be 10.
Don't worry, don't worry. Figure 5.8 in page 6.
Page 60. Yes.
Did you find a relationship between early reactions and fuel composition? I mean, oxygenates and
of course.
and aromatics.
Yeah.
Something else or need those, the presence of aromatics and oxygen. That's the thing. Do you think there is something else?
No, there's something else. N-heptane has a significant role in increasing early reactions, and toluene and ethanol are or having a role in suppressing the early reaction. So basically, when we increase the ethanol or toluene or aromatic or oxygenates, because they act as radical link for low temperature reaction, they consume the species that we need for early reaction, they suppress the early reaction. But instead, N-heptane will generate more of those radicals, and we will have higher heat during the early reaction.
You mentioned that the Lund sensitivity number is influenced by the pure composition.
Exactly.
This is in page 3.4. I don't think you need to find it here.
Yeah.
But looking at the expression, it only includes compression ratio and sensitivity, not fuel properties. You can have two fuels with showing the same compression ratio, but having different fuel properties.
Yeah.
Or fuel composition.
I'm sorry, I didn't get your question.
You said that Lund sensitivity number is influenced by fuel properties.
Yes.
But I cannot see the fuel properties in the expression, because compression ratio is related. You can have different fuels showing different fuel compositions, but showing the same compression ratio.
Yeah.
So why did you say that? What were you thinking about when you wrote this?
I'm still not sure if I understood your question correctly, but I try to explain it to clarify. Lund sensitivity number depends on fuel composition. It means how much ethanol do you have, how much oxygenators do you have, how much aromatics do you have, how much N-heptane or different hydrocarbons that you have in your fuel will affect the feed sensitivity. I understand that we might have the first initial compression ratio similar for different fuels with different composition, but it doesn't mean that if we sweep feed, we also get the final compression ratio the same for both. So the variation of compression ratio is the point, not the value of compression ratio for each feed.
Okay. Can you go to page 62?
Yes.
Figure 5.9.
5.9, yes.
When you compare the Lund sensitivity number with other fuel indexes, I cannot see homogeneous trends.
Yeah,
so,
there's not any trend.
But so what does it mean, that the other indices are wrong?
No, no, they just want, that was important to present it here, because we don't want to repeat the values or the work that other people done in different way. I try to say here that my former colleague have developed Lund Chevron HCCI numbers. It's a very valuable number, but this number, it works well in HCCI combustion for definition of auto-ignition property, but it doesn't say anything about when we have the feed sweep. This was what I want to say. Or S, which is very valuable. The differences between RON and MON is again the same. They did a lot of valuable research, but again, it doesn't say anything about what we have when we have feed sweep. And heat of vaporization is just some physical values, physical property of the fuel. But again, it doesn't lead us directly to somewhere to know something about feed sensitivity. This is why it's important to have feed sensitivity test method. Yeah.
Why didn't you include an NOx tendency plot? You have included several plots about emissions, but not NOx, not CO. No, I mean, for CO you did it, but not for NOx. And NOx is also increasing the climate change, not as much as CO2, but because there are less around. So why not? Why did you?
Because the HCCI combustion is below to 20 ppm or 50 ppm. So it's just like even we breathe, measure in this air, I don't know how much ppm would be at the NOx. So it doesn't really make sense. It is really comes out of the engine, or it's just, yeah, it's too low for ICCI combustion. It's less than 60 ppm or something like that for my experiment. So we decided with my supervisor that it's nothing to present.
Okay.
Yeah.
I understand a stoichiometric reaction, but I don't understand when you said since the stoichiometric value of the blend is increasing, what is the stoichiometric value of a blend? I don't know what it is.
Yeah, I mean, for different fuel, we have different stoichiometric ratios. I meant this ratio. For example, the stoichiometric ratio of N-heptane is different compared to ethanol. And therefore, you need more ethanol to have the same phi compared to N-heptane. This is why fuel consumption for those fuels is also more. Because ethanol has some oxygen content, then it makes the mixture lean itself. So you have to add more and more carbon to get the correct or favorable stoichiometric ratio.
Okay, so you were thinking about the oxygens you would need for the combustion. When you said the stoichiometric value of a blend, you were thinking about the combustion itself.
Yeah, I want to say the stoichiometric ratio value, the number itself, this number that we have for a stoichiometric ratio of each fuel.
Okay.
This is the number.
Yeah, okay. So maybe because you wrote value that I was.
Yeah, I'm sorry.
Don't worry. Yeah. Your conclusion number 5 said that on page 81, if you want to see. You said Lund sensitivity.
81. Yes.
Condition number 5.
How does the blending?
On page 81.
Yeah.
And conclusion number 5 said Lund sensitivity applied to alcohol blends. Conclusion number 5 in the final chapter of conclusions.
Yeah.
Anyway, you can.
Yeah.
For sure, you can answer it.
Yeah.
You said Lund sensitivity applied to alcohol blends do not exhibit linear behavior.
Oh, yeah.
Is this a drawback?
No.
Because if it doesn't show you a linear trend, how can you interpret the results? So.
No, it's not a drawback. It's just a property. We have it the same with octane number. We know that sometimes if you add 10% of ethanol, you might get higher octane number of the blends, or almost a similar of adding 40% ethanol. This is the same with phi sensitivity. If you add, for example, 10% isobutanol to a blend, you may get more phi sensitivity compared to 80% of isobutanol or N-butanol. It's not the numbers are just something to say, not the exact number. It is not a drawback. It is a knowledge that helps us how to tailor our fuel, because then we know, okay, if we need more oxygen, we can add more fuel, but we don't get more phi sensitivity, which is good, for example, for SI engine. Or or the other way around. It's just some information that you can play around and design your fuel.
I bet it is confusing for you now. Yeah, in your conclusions that you have shown us in the presentation, I found that 2 of them were very similar or the same.
Yeah, do you want me to show them on the screen? Here or the previous one?
Yeah, this one.
Yeah.
You say with different temperatures,
Mm-hmm.
you got in both cases the maximum Lund sensitivity number.
Yeah, but for different composition. The first one has tolu and ethanol reference fuel.
Yeah.
But the second one doesn't have oxygenates.
So the conclusion would be, no matter which temperature you have, the learned sensitivity number will show you the maximum value.
No. This was not my intention. I want to say that at low intake temperature, in each run group, the Lume sensitivity number is maximum for a fuel which has all 4 components. But at higher intake temperature, for each run group, the Lume sensitivity number is maximum for 3 component fuels.
Yeah. So if you were asked to choose just 2 conclusions from your work, which will be these 2 main amazing conclusions from your work?
I think I choose it from the previous slide, maybe. This one. This 3, 1, 2, 3. If I want to choose 2, then 1 and 3.
1 and 3.
No, 1 and 2.
1 and 2. Okay. And the weak point of your thesis, what would be?
I wish there was technical possibility of having an extended range of feed. And also, I wish if I had time to tailor some fuel and test it in other test cells with the Volvo or Scania engineers, the conventional engines that we have.
Do you think that your contribution could have relaunching these combustion engines?
Yeah, I think what I have explained and what I have developed, of course, might not be perfect, but at least is an opening for such a valuable or such an important property to be understood and measured by technical people in refineries. So next time, if we use this method, it would be difficult to say that, sorry, we don't have equipment to check if this fuel fits your engine or not. You should find a way to do it yourself. But then it would not be the case. We can easily call Seibold company that have CFR engine in Sweden and ask them, would you please measure run number and also fit sensitivity of this fuel for us? We want to see if it fits your engine.
Do you think in this sense, it would be valuable to provide maybe a long table with potential values of depending on the composition of the fuel that are good for this kind of engine or not?
I think it's not that. No, I think it's not valuable.
No?
Because preparing such a table with all of those details might always have some error or mistake, and it's also take a lot of time. But you can easily send fuel and they test it, and then you will see if it fits or not. And then you have also the backbone. You know that you need aromatic, you need oxygenate, for example, or those and those. And then you have a kind of big picture, and then you just send it for a company and they measure it and send it for you. Because this is, then if you want to do like what you say, then it would be something like numerical study. Then we need a very just like big database of, I want to make it simple.
Or not. You can use near-infrared spectroscopy. I don't know if you know it, this NIRS.
No.
And then you can use it after training the machine. You can use it and just with you push the button over the fuel and say good or not for the engine, or it can provide you with a number. It can provide you with a number and say this sensitivity, this speed sensitivity number. Yeah, you can have it. We are working on this.
Oh, that would be nice.
This kind of machine, yeah.
Yeah. But then you need a long list of all of the details
You
that
need-
contributing. But then we don't know what would be the co-effect.
Yeah.
Yeah, because here, for example, when we have ethanol, we have some impact. But when we mix ethanol with toluene, we will see another impact. So we cannot always just, I don't know how to say, it's not always a single impact that, okay, if we increase ethanol, would be like that. No, because it also depends on the rest of the components in the mixture.
You mean side effects?
Yeah, yes, or co-effects that some two different composition together will have on the result parameters.
Well, this is an statistics
Yeah.
model. So
Yeah.
you can also train it for this.
Yeah.
You know that it will happen.
The co-effect, yeah.
Yeah.
That would be
So
interesting.
You can have, you need to have many data, and
Yeah.
after this you can apply to much more, many more data. So
Yeah.
it's just an idea.
Yeah, that would be very interesting to know more about that.
Are you planning to continue these experiments, or are you going to just stop here and start another thing?
I would really like to continue working research, and I'm looking for opportunities.
Very good. Okay, so again, I would like to thank you and to congratulate you. I think you have done a very nice work. I enjoy a lot reading your manuscript. And well, your manuscript, your document, because the manuscript from this, the work from this are very good, in very good journals that, as I told you, only with this, you have already the PhD degree, you know, only with this, because they were peer reviewed by people from everywhere, anonymous people. So really, congratulations.
Thank you. Thank you.
And I wish you very good luck in your future.
Thank you. It's my pleasure. And thank you for your time and evaluating my work. It means a lot to me. Thank you very much.
Thank you.
Thank you.
Thank you. This part of the session. Now we will continue with having a small break, just for 5 minutes, I guess, and then we'll continue with the grading committee questions. Okay, welcome back. Then I will continue with the questions from the grading committee. I don't know if any one of you are very eager, otherwise I will start from the left with you, Petter.
Okay. What should we start with? Let's see. Yeah, can you draw like a load speed diagram for an HCCI engine and show me where you can run HCCI?
I
mean, if you have like a loads, all engines, they have like a load speed diagram. You have like a maximum torque curve, maximum how much torque you can get. So you have a maximum curve, and where can you run an engine in HCCI, and can you elaborate a little bit on that?
I will try.
Yeah,
but I cannot promise.
Oh, sure.
Just with those kind of
so your load or torque or
then
is in
load,
and speed.
and this is the speed.
Yes. Okay.
That's very
So if you run an engine with HCCI,
we always run at low load with HCCI.
Yeah.
And this is one point about HCCI combustion, that we cannot increase the load. And the reason that we cannot increase the load is that in HCCI combustion, because it's a kinetic driven combustion and it's based on auto-ignition, if you increase the load, the pressure raise rate would be so high that it would be just like knocking. It is not something like combustion, that you cannot really generate power out of it. This is one reason. that we always run SCCI at low load, but it doesn't mean that SCCI is not a useful combustion technology. Beside this fact, if you remember the bubbles plot that I had in my presentation, I showed that the limited load range is one of the problems that we have with low temperature combustion. But how we tackle that? If we come back to my conclusions here, low temperature gasoline engine. The LTC engines are some engines that they combine different technologies sometimes in them. It means that for low load, they use HCI combustion with early injection, have homogeneous without a spark plug. And when they need high load, they do the same with homogeneous, increase the load, but instead, in a good timing at a high load, they will use a spark plug to burn it, and they will have a combine of both low load and high load in XCCI. But generally in XCCI, the highest load would be considered 0.4, be high load for XCCI, and we cannot run more than linear than 0.25 because we will have a lot of misfire.
So what I want this to lead to is that you probably need to operate engine in another operation mode, like maybe you have like a direct injection diesel, or maybe you have SI, homogeneous mode. But then at those loads, I mean, in your area where you look at HCCI, NOx is not the problem.
No, not at all.
Particulates is not the problem. Everything
Exactly.
is peace. It's really good. But then you need to increase the load, and then other things start to become a problem. And I wanted to elaborate a little bit on the phi sensitivity. Is there a limit on the relevance of phi sensitivity? Because if you can take whatever type of fuel you want, and you can burn it in an internal combustion. You can adapt the engine in some ways.
Yeah.
You can like you have different combustion timings and so on. But still, you need to also run the engine at higher loads. And what about phi sensitivity? Is it complete enough? I mean, what happens if you have full load, for instance? What problems of emissions do you have then?
Yes, that's a good question. If you start with the storyline that I had in my presentation, I talk about it that when we have internal combustion engine, if we want to use them as an enabler for sustainable development, sustainable transport system, then we need to increase the efficiency and lower the emission. And one of the options for lowering the emissions is using LTC combustion. So I'm not talking about all of the options that we have, because I'm concentrated on low emission, high efficiency combustion concept, which is LTC. And I try to, because already we have cetane number for compression ignition engines, and we have Calgary index, we have Tuluan index, we have SCCI index, we have Lund Chevron SCCI number. We have all of those. They're working for different concepts, but we were looking for something that can explain the stratified combustions at low temperature regime. That was why my method is very specific. I'm not sure what will happen if we increase the range of phi to the rich zone, but this is not favorable, because in the rich zone, as you said, we will have soot, we will have NOx, and we will also use a lot of fuel. Our objective is just get the most out of the fuel that we have.
I mean, for SI engine, for instance, I mean, if you have quite different fuel, you blend a little bit here and a little bit there in different fuels. The main difference in the combustion and emissions would be particulates. Now, in SI engines, it's incredibly high injection pressures and so on. So, I mean, you have tested a lot of fuels, and do you have any ideas what will that lead to if you don't take the phi sensitivity into account, if you just take other problems that might occur in an engine, like soot, for instance? What does it mean for such engines where you have soot problems? Is it
I'm sorry, I didn't get your question. You mean that?
I mean, you mostly looking at auto ignition stuff,
Yes.
like could you, for instance, have done this in a spray chamber? Do you even need an engine to do it? Because you want to freeze your condition to a certain, you want to have homogeneous, very homogeneous mixture, very controlled temperature, and etc. etc. Could you have done it in a spray chamber instead? I'm just challenge you.
Yeah, no, yeah, I understand your question.
So is an engine needed to do this?
The thing is that we need to define a standard test method that needs give possibilities to refinery and fuel industry to apply it easily. And C4 engine is a test facility that is already available almost everywhere when people are producing fuel or working with fuel in different labs. We have it there, and we have technicians that know how to work with that. Then it would be really, I think, when we want to give a solution, the important point is that always the best solution is not the solution that has the most accurate data or something like that, because it's also important that how this solution can be used. If you give a very difficult explanation to something, or for example, to a kid for a scientific term that he or she even cannot handle, then this solution might be completely wrong, right? This explanation that you give, but it's not possible for him or her to explain it to someone else or to use it even. Then we need something to be technically simple to implement, and we need to have it or to work with it with already in place test facilities. That was the intention. It was not just about designing a method that can measure the feed sensitivity, for example. Designing a method can measure the feed sensitivity, usable for refineries, be easy to apply for technicians, and get the result in a quite fast way.
Do you agree that that might be other like a response variables such as SUD can be also extremely important apart from feed sensitivity?
Yes, definitely. But this is the second point.
Yeah.
First, we need to say, okay, this fuel in terms of combustion capability burns in this engine. And then we look at, okay, now we can burn this fuel in this engine. Let's look at the emissions. What kind of emissions do we have? Then, based on that emissions, we can retailor the fuel, measure the feed sensitivity again, and use it in the engine and test the emissions again. So basically, I want to say this feed sensitivity is just like a pattern that you use to tailor a clothes, and then you just need to try it to see if it fits or not.
Yeah. You have like 4 PFI injectors to inject the fuel in, and so do you have any idea on how homogeneous the mixture will be in the engine? Or is it that an assumption that you have like a fuel injector upstream and then will vaporize and mix, and we assume that it is?
Yes.
But is there any measurement?
No, it's assumption. Exactly. We have port fuel injectors, but we only use one injector at a time. So it means that when I want to blend, I blend the fuel manually. It was not using those injectors. And then it is after the heater, located after the heater. So the already warm air is coming in, and then we inject the fuel, and then we have pressure sensor, intake temperature sensor after the injector. So we assume basically that the fuel is homogeneous.
Yeah, I think it's true, because I mean there is a huge difference between direct injection and port fuel injection when it comes to homogeneity. Definitely, yeah, I agree with you. I think it's a fair assumption. This engine with assessment of fuel, is that if you would have designed a new engine today, how would you have designed it, and what is there any like a weakness on the engine that significantly would have changed your results in some way?
I would like to have an engine with a wider range of compression ratio, like instead of 18, something like 25 or something like that for the maximum compression ratio. I think that was the most thing that I would like to have on the C4 engine.
Okay, Nika, thank you very much.
Thank you very much.
I think we'll just continue.
Okay. I would like to divide your thesis into a soft part and a hard part. And
Yeah, of course.
particularly, I really liked the presentation, so I would like to have a copy of it if you allow me to.
Sure, of course. I will be
Because
happy.
it links the parts together very well. And I'm mostly involved with the hard part, and I find it difficult sometimes to obtain interest from the general public about what I'm doing, but doing it the way you did there might increase my possibilities.
Thank you very much. My pleasure. Thank you. Sure.
But of course, I have mostly questions for the hard part, but I have one question for the soft part. I saw your presentation of the forecast for electric vehicles and internal combustion engine vehicles in the future.
Yeah.
So I would like to know where do we have it from, and what are there many uncertainties related to such a forecast?
That is from a Bloomberg report. I have the data. I think it's for 2020. This report. I can forward it to you also if you want. Yeah.
Many of those.
Yeah.
But what are the main? I mean, is it for certain that it will turn out in that way in the future, or what do you think? Are there any uncertainties on the way? And so
there's always.
It's completely different developments. Or what?
Yeah, there are always uncertainty in any model, I would say. We can never predict everything. It's just 100%. Even this time stability plot or model that I had here, this is also it's just a model that someone proposed based on some assumptions. That models are always based on assumptions, and we just can. I think the only thing is that we know that if we have this assumption, that would be the scenario, but it's not that definitely that would be the scenario in any cases. No, it's never the point. But especially about share of combustion engine in the future, I think we shouldn't just look at Nordic countries or even Central European countries. If we look at some places, some remote places in Africa, for example, they still even don't have normal car that works with combustion engine. How we can imagine that we will provide the infrastructure for charging electric vehicle for them by 2040, for example? Or if we look at my country, Iran, then when we have a lot of fossil fuels, how we expect that the government, hopefully the next government, will agree on investing a lot of money on developing new infrastructure for electric vehicle instead of just using the in-place infrastructure of liquid fuels. The thing is that if we just take Nordic countries, it looks really nice and clean. And okay, we might be 100% electric by 2030, even in Nordic countries or Sweden or Norway. But the world is not only Nordic countries. We are all in the same boat, and we cannot just fix our place and just let the mess to be in Africa or I don't know, the other places. I think we need to think global. And if we think global, then we can see that the challenge is global. The solution must be global too. Then I think we need combustion engine, and we need to improve it to be able to serve sustainable development for people in poor countries.
Thank you. Very good. answer.
Thank you.
And you may think about China. You imagine the infrastructure, electricity working there.
Yeah,
It will take a lot of time.
yeah, exactly.
And yeah, there are many other. But I agree with you. That's the infrastructure I think, in countries that does not belong to North America or Europe will be critical.
Yeah, exactly.
Okay. Your hard parts about the experimental part,
Yes.
you conclude that this is method. Are you sure about that? I mean,
Yeah, the measurement.
CFI, first of all. And the CFI indeed is normally used to estimate octane number and cetane number.
Exactly.
And in order to make it faster, someone invented what we call the cetane index, because that's much faster to estimate compared to cetane. So this phi sensitivity number, do you see any possibility to estimate this in a similar way, much faster way?
Even in terms of time.
Using an internet, we use physical chemical properties of it's investigated a lot of things. So
Yeah.
will it be possible to estimate this from fuel specifications? You think?
I think this is what people do with numerical study, but it's not faster. They, but from physical or chemical properties of the fuel, maybe a complex model consists a lot of physical or chemical properties, something like this, what Optima group are working on, maybe something like that. But in terms of being quick, the method development was not quick, of course. It took almost 6 years, but then the application of it is just for one fuel, 2 hours or less. Yeah, but all of the refineries, they have CFR engine. All of the labs and every industry that works with fuel production, they have CFR engine. But if you mean the industry, the university, then we also send our fuel for run and mon measurement to different labs. Like what I did, even though I had a CFR engine in the lab, but to save the time, I just send it to Seibold, the project partner, and they measure it for me. I think would be also an option in the future if we want to think of phi sensitivity method.
So your work was mainly experimental.
Yes.
Many researchers use modeling as a basic tool. Sometimes your explanation is especially in terms of 5 a bit complicated. And I almost forgot most of it after reading the chapter, but I guess I could, that's maybe my mistake. But could you have, instead of these, sometimes speculation and used modeling to, for instance, tell about the influence of temperature? If you model the temperature at the end, couldn't that have given you many explanations?
I didn't do that, yes. My work was mainly experimental, you're right. Yeah, it might give, definitely, modeling will give a lot of valuable information about how the things are happening, but I didn't do it.
No, but that could maybe be one of the
Another step, yeah. Yeah.
So, yeah. I didn't see any graphs showing efficiency as a function of sensitivity. Is that possible to do that?
Yes, but the thing is that because CFR engine, first of all, we know that I have it in some of the, I think it is in the second paper or third paper, something. No, it's COBI. The thing is that the efficiency of SSCI combustion is generally very high. Its combustion efficiency is very high. And since the SSCI engine is not a conventional engine, is not relevant to have engine efficiency for that. And then I was doing sweep. It would be very valuable to do that, to just take different fuels with different feed sensitivities with the same run number, test it in a normal conventional engine, and then measure the feed sensitivity. But with my CFR engine, or the CFR engine that I was using, sorry, telling of course it's not mine. With this CFR engine, it was not scientifically valuable to do that. It was just, but it would be very valuable to tailor fuel with different feed sensitivities, send it to one of the other test cells that we have, and then measure the feed sensitivity, the efficiency there.
No, I did some research on this some 30 years ago on burn hydrocarbon as it was. We may be able to answer some of the questions that's myself at that time. But you know, we divided the compression.
Sorry, would you please?
We found that the important mechanism for burn hydrocarbon emissions were actually due to something called post-oxidation.
Yes.
And we say somewhere that the decrease the compression ratio, the ongoing hydrocarbon decreases. And
yes,
we actually at that time found that this is because the temperature for combustion, post-combustion is lower, because we have a very efficient main combustion, and there's not that much energy for the post-combustion. So temperature goes down, which is why emission in ongoing hydrocarbon emission increases with increasing compression ratio. So I think that's the main reason for the influence of the compression ratio. But you didn't look into post-combustion influence of these emissions that you have picturized here.
Yeah, the thing was that I have studied emissions also, but I couldn't find any direct link between emissions and feed sensitivity, or I couldn't use them as an indicator or anything like that for feed sensitivity. This is why they are not included in the main body of the work. But what I can say about unburned hydrocarbon and SSCI combustion and why it increases or decreases and so on, the thing is that SSCI combustion has very low temperature inside the combustion chamber and also very lean. There is always risk of incomplete combustion. And because it's homogeneous, we always have some charge that are in services area, and they don't engage in the combustion at all. And it's just coming in, going out directly because the inside temperature is not that hot. But in my case, because I'm using the CFR engine, then I increase the compression ratio. Maybe I can have some drawing of the CFR engine, how it works. Because I think some of the emissions that I have is mainly connected with the geometry and the engine itself, yeah, the engine itself, the different changes of different parts, it's not all about the combustion. If this is the, yeah. Center here. This is the condition that we have at high compression ratio. The clearance gap is very small. But when we lower the compression ratio, because the, the stroke is the same, or the sweep volume is the same, what the engine does, that lifts up the cylinder head, and you can see it is really interesting when you increase this is why I say that it's an engineering masterpiece, because you see that the cylinder head is going up, and then the cylinder head is going up, and then you had larger clearance volume, and therefore you have lower compression ratio. This property itself is the reason for many of different things that we see in the in the emissions of specifically unburned hydrocarbon, and how it increases and decreases because the volume of the gas that we have inside the combustion chamber is changing during changing the compression ratio. I think this is important too. The important point. Yeah.
But at that time, we found that the temperature is really a key parameter.
Exactly. 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 It is. I don't want to say that it's not. It's definitely it is. And we also, when we increase phi, we have higher in temperature inside the combustion chamber. Then we expect that the unburned hydrocarbon decreases. But because when we increase phi, we also increase this volume, then they compensate for each other. Yeah.
Just to round up this discussion, overall, I think your conclusion was that unburned hydrocarbons increases with the lower feed sensitivity, and carbon monoxide is the opposite. So usually they follow each other. Can you give a quick
Can you just,
why this is the case?
yeah, in conclusion, would you please give the page number so I can have a look on it?
I think it's on page, it's the chapter from page 67 to 68. Your conclusion regarding unburned hydrocarbon is that it increases with lower feed sensitivity, and carbon monoxide decreases with lower feed sensitivity. Or did I miss something?
Okay.
You don't need to give an explanation. I was just wondering because they usually follow.
Sorry, I cannot find it. Then it says that it's page 69.
On the last page 68.
68.
Says,
Oh, decreasing the compression ratio.
the last two lines. Yeah, somewhere in the chapter about hydrocarbons, the opposite trends with hydrocarbons.
For CO and unburned hydrocarbon.
But it might be hard to explain. So I didn't think you did any attempt to explain it. So I just wondered if you had it.
I think I can provide. Yeah, I of course. I think I can provide explanation. Just if you give me some seconds. Thank you. Oh, okay. I think this is the the CO emissions decrease in response to increase in phi, not increase in phi sensitivity.
Oh, okay.
Yeah, so when we increase the phi, when we sweep the phi, all of the blends, the CO emissions increases for them. Then it's phi, it's not phi sensitivity. Sorry if it was not, no, this maybe my writing, it was not that clear.
So I'm gonna shut up.
Oh. Thank you very much.
My questions.
Thank you.
Well, and I'm quite sure you wrote the thesis. I think you have a complete overview of everything. Thank you for that.
Thank you. Thank you very much.
Okay. So, the one first one behind you and the rest of your life. Okay, I have a couple of short questions. Following up on the last comment from your opponent, you mentioned that we'd like to investigate a more extended range of light.
Yep.
How extensive range? How extensive range would be interesting for your?
Stoichiometric.
Yeah. Okay. That's,
Yeah, because I think phi sensitivity study is very valuable for SI and avoiding supernoc. Then it would be really interesting to study it close to stoichiometric.
Or would it introduce additional challenges in the lab?
The method need to be not the phi sensitivity method, but the way that, because we cannot run XCI in a stoichiometric. It's just such aggressive combustion. But that's what some other researchers are doing in other universities, is that they start SCCI, they get the low temperature reactions, and then they burn the rest of the fuel. So they avoid the excessive pressure raise rate. In this way, they try to study the early reactions close to stoichiometric, but in this case, we cannot have the compression ratio that auto-ignites the fuel. I don't have any idea yet, but we did some, I mean, not me, as my colleague in Valencia University, they did some numerical study that it's also, the paper is presented in my thesis. I only did the experimental part, but the idea was that if we can extend the range using numerical study, but still, I cannot think of any way that I can do it experimentally yet.
And now you're actually touching upon another question that I have. Also following up on some other questions. Would it be possible to reach your results using numerical methods?
Yeah, it shows that it can.
So we're all suggesting that we should work in a different way. Are there potential limitations to that?
I try to address, when I was designing my experiment, I was talking with Professor Bai, I think he is not here now, and ask him, excuse me, how I should design my experiment to be usable later for numerical studies. And then he told me, avoid the combustion phasing later than 8. And then when I was trying myself, I saw even 8 was not appropriate. And it was a lot of combustion instability. So I kept it up to 6. And I think my data are valid for numerical evaluations and, or let's say, just for modeling. Yeah.
As you say, it might be a way to extend the range.
Yeah.
You can validate your models with the present results.
Yeah.
Okay. You use or discuss, mention something that we call low temperature combustion.
Yeah.
It's a very common concept, and everyone talks about low temperatures, intermediate temperatures,
Yeah.
high temperatures. What is low? What is a low temperature combustion? What is it a specific temperature, or how would you define why are you allowed to call a combustion scenario low temperature?
Oh, nice question. Yeah, actually, because it's a kinetics driven combustion, or the low temperature, ACCI specifically, the reactions start from almost 550 degrees Celsius, the significant one, and up to 850, if I'm not mistaken, we have the early phase of reaction. And by 1500, if I'm not mistaken, the combustion is complete. This is one specification of low temperature combustion.
And are you not talking about a particular fuel?
No.
Do you think there are like distinct temperatures where you say for all fuels it's low temperature combustion under this temperature? Is there such a temperature?
I think it makes sense to have it like that. When I was testing, it's from 550, yes, Kelvin. It's Kelvin. Sorry, I mixed up a little bit. Yeah, just skip it. For 550 to 850. It's quite wide range. And then we have the early phase of the combustion done. And then below 1,500 or 2,000, then we have a complete combustion done. I'm sorry, that cannot provide more.
No, nice.
But I would be happy to discuss more if you have more questions.
I would say it's difficult to set a certain temperature that would be true for all fuels or all conditions.
Because it's a range.
Yeah, it's a range.
Yeah, it's a range. It's not just exactly this temperature or that temperature. It's a range from this to that. And then we hope that the early reaction starts, because we know the mechanisms and how the chemical reactions are, the need of chemical reactions to temperature.
Exactly. So now you're onto it, because it's actually the nature of the chemical reaction in a certain temperature regime that makes us call it low temperature.
Yeah.
Yes. Okay. A final question, I think. Yeah. Or two final questions. No, I will have just one final question that you almost touched upon. So who is the user? Who is the main user of your results now?
Now you mean?
Like in a short term and maybe in a long term.
In short term, my colleagues, or then my colleagues today, of course, I would be not with them later on, but I think they can benefit from that a lot. They can design fuel based on my method, test it on my previous test cell, and then test it on another test cell to see, to look at the emissions and so on. Also, everyone who's interested in numerical study can use my experimental data. And later, maybe we can talk with some fuel industry or refinery, present it to them to sell our idea to them. I don't know, but it would be more long term.
What more work will be required before we can do that? Not easy to answer.
You mean before making it commercial? Or?
Yeah, exactly. Because you talked about that it could be a method like
Run or man.
Yeah, but what more needs to be done before it's, or is it just a matter of selling it and convince people? Or do you have
No, I think it's just not only the matter of selling that.
would you need to extend the range of fuels or something, or prove it better, or what would you need to do before being able to go to commercial use?
So I think the range of the feed is acceptable for low temperature combustion, and this was our focus at the moment. The only thing that I think I need to prepare a kind of handbook with the changes that they need to do to the CFR engine, and very detailed all of the things like air temperature, air humidity, something like run and Montes, to make it more, to just try to remove the impact of any environmental changes or on the result parameters, like exact temperature, how should be the exactly the coolant, and all of those details that need to be specified, which is in my experimental reports that I have, but it's not in one place as a document for someone or for a company. It is available in my thesis, all of it almost, but then you need to, write it in a different way. Yeah.
Okay, thank you.
Thank you. Thank you very much.
Thank you. So now we actually open up the floor for the audience to ask questions to Nika.
Thank you. Yes.
Since I read your work.
Thank you.
Or tried to in a couple of days. It was very interesting, not my subject, but I wonder about, you're writing a lot about electric cars and the negative things about that.
Mm-hmm.
But when you look at biofuels,
Yeah.
what are the negative impacts with your
Mm-hmm.
said something of land use or food? But would there be enough biofuel to would there be enough biofuels in the future for, we say we have more population and we have developing countries wanting to have more engines?
Mm-hmm.
How do you look at that?
Yes, thank you very much. First, thank you for reading my thesis. This was just a short time. Sustainable transport sector doesn't mean one electric car for every person. Doesn't mean one car for every person. Sustainable transport system is a combination of different things. If I want to look at it from a bigger picture view, we need to improve, even in Sweden, we need to improve the public transport, make it cheap, available for everyone, increase the frequency. And this is one thing which is really important. We shouldn't think that how we can give everyone one car. This is the only way to make it. No, this is not, that we should forget about those things. We should try to convince people and society that don't buy more. Just try to look at other options, like having a pool of car. When you need, you rent, and then you leave it there. You don't need to own a car. And then in this case, we just reduce the amount of material that we just take out of the earth. We reduce a lot of that, and we control that with just improving public transport. Just after COVID, we had such a nice outcome, though it was difficult. We lost a lot of lives, but we understood that people can stay at home, stop transporting back and forth, burning a lot of fuel, and still do the same job. I think we need to decrease the amount of transport that we need in different ways, put it on the shoulder of public transportations as much as we can. And then when it comes to necessary personal transportation, like personal cars or something, we replace it as much as possible with biofuel, and then, sorry to say, electric vehicle. Because I personally think we don't have enough rare elements for give every Swedish citizen or every Nordic citizen one huge battery, but one for the fuel cell that they have, sorry, solar cell that they have on the roof, and one for their car. I think we should think, yeah, we should be realistic with what we have, and also the damage. We do a lot of mining, it's contaminating soil. A lot of children are working there in the mine just to us breathe more fresh air. I think we should change the way that we think.
Thank you. I'm glad to hear, because I mean, working with energihushållning, energy management planning, you are looking at substitution here. You
Yeah,
also have efficiency and you also have saving. And I was happy.
yeah, thank you, Shasta. Thank you very much. Thank you.
Right, going first. Second. Then I will ask a question, if there's no other questions. What was the most fun during these years during your PhD?
Oh, I had a lot of fun moments. I don't know which one. I think the last day that I collected the last data that I need for writing my thesis was one of the more exciting moment, if I can say. But generally, the time that we had more colleagues, the lunch that we had together in Finin were, yeah, something that I will never forget.
Nice to hear. Okay, with that, I thank you, Nika.
Thank you.
And the opponent, and also the grading committee, and also the full audience that are here today. So this closed the public session, and we will, the grading committee and opponent will follow me to a closed session where we'll have a discussion about the verdict of Nika's work.
Yeah.
And we'll then meet in the lunchroom to give the decision. So let's close this session with a round of applause to everybody involved.
Thank you.